to Starry Cosmos. For millennia, the gaze turned upward, seeking an edge to the dark expanse above. A persistent question whispered through generations. What lies beyond the furthest visible star? Now we find ourselves at a point where that question takes on new weight, new clarity. Scientists paint a picture of something almost unimaginable, a boundary defined not by distance, but by the very light itself. Light from the most distant objects has traveled for billions of years to reach us, and it tells a story of expansion, a constant stretching toward an unseen horizon. It is a place where our understanding falters, where the known dissolves into the profoundly mysterious, a realm hinting at beginnings beyond our current comprehension. So dim your lights, settle in, get yourself comfortable, let your breathing slow, and let us begin. If these quiet journeys help you drift off, take a slow breath and subscribe to Starry Cosmos so the next one finds you when you need it. Consider settling into a comfortable space as we begin to contemplate something profoundly distant, a boundary that stretches beyond our immediate perception, pushing against the limits of what we can truly know. We'll journey toward an unseen horizon, one defined not by solid walls or tangible barriers, but by the relentless forward march of existence itself. It begins with the understanding that space, and therefore everything within it, is not resting still. It is continually evolving, relentlessly expanding outward from every conceivable point. This isn't a simple stretching out like an elastic band, but rather a swelling, a constant increase in volume, a cosmic inflation that has been occurring since the very beginning, a legacy of the incredible energy unleashed during the Big Bang. To grasp this expansion accurately, we must turn to a key measurement, the Hubble constant. Scientists have painstakingly refined our understanding of how quickly the universe is growing through observing distant objects, galaxies seen at immense distances, and therefore far into the past, and measuring their recessional velocity. Currently, the most precise measurements suggest an accelerating expansion rate, indicating that the Hubble constant sits somewhere around 77 kilometers per second per megaparsec. A megaparsec is a unit of distance, approximately 3.26 million light years. A truly staggering scale to contemplate. It's a number that represents the speed at which these distant galaxies are moving away from us, with each additional megaparsec of space separating them. A rate that, when compounded over billions of years, reveals just how incredibly fast the universe is expanding. But simply knowing that it's expanding isn't enough to truly comprehend its implications. We need a way to witness this expansion directly, to demonstrate that it's not merely a theoretical construct, but an observable reality. That's where the concept of redshift comes into play, a phenomenon first described by Vesto Slipher in the early 20th century and later formalized by Edwin Hubble himself. Redshift describes the stretching of light waves as they travel across expanding space, much like the sound of an ambulance siren changing pitch as it moves away from you. The higher pitch representing a decrease in wavelength. The longer wavelengths of light emitted by distant objects are stretched, shifting them towards the red end of the spectrum. The greater the distance to the object, and therefore the more redshifted its light becomes, the faster that object is receding from us. Think of it like this. You're standing on a hilltop and shining a flashlight forward. As the beam travels outward, the space between you and the target expands. The light waves stretch out as they move through this expanding space, becoming slightly longer, redder wavelengths. This isn't an inherent property of the object itself. It's a consequence of being embedded within an expanding universe. Every distant galaxy we observe exhibits redshift, a subtle but unmistakable signal that confirms our fundamental understanding of cosmic expansion. This constantly accelerating expansion defines what we call the observable universe, the sphere of space from which light has had enough time to reach us since the Big Bang. Imagine standing here on Earth, and you can only see as far as light has traveled to reach you in 13.3 billion years. Because the universe is expanding, that horizon moves further away with every passing moment. Light emitted from galaxies beyond this horizon simply doesn't have enough time to arrive. These distant galaxies are receding faster than the speed of light, not through space, but rather carried along by the expansion of space itself. It's a crucial distinction. We aren't observing these galaxies directly. We're detecting the echo of their existence, the faint, red-shifted light that was emitted long ago and is now reaching us after an incredibly lengthy journey. The boundary of this observable universe isn't sharp or rigid. It's more like a fuzzy sphere, continuously expanding as new light streams in from regions beyond our current vantage point. What lies beyond this horizon remains shrouded in mystery, inaccessible to direct observation. Hypotheses abound about what might exist there. Perhaps another, separate universe, or simply an infinitely expanding void. But for now, all that we can truly know is defined by the light we are able to perceive from the distant edges of our observable cosmos. It's a humbling reminder of both the vastness and the limitations of our understanding, urging us to continue exploring and refining our grasp on this ever-evolving universe of our observable cosmos. It's a humbling reminder of both the vastness and the limitations of our understanding, urging us to continue exploring and refining our grasp on this ever-evolving universe. Now, let's consider what that vastness truly means when we begin to contemplate the edges of what we can perceive. The distance itself plays an enormous role, but not in a simple linear way. We often think of space as simply an empty void, and the farther something is, the longer it takes for information, specifically photons, to reach us. But that's a simplification, easily clouded by concepts like time dilation. Einstein's theories of relativity tell us that time isn't absolute. Its passage depends on your relative motion and gravitational environment. As you move faster through space, time slows down for you compared to someone who is stationary. And as you experience a stronger gravitational field, time also slows down. This doesn't affect your personal experience. You wouldn't feel time slowing, but it does change the rate at which events occur and how they are observed from different points in space-time. The farther away an object is, the more its motion contributes to this effect. Imagine photons emitted from a galaxy located billions of light years away. They began their journey long before our solar system even existed. As these photons travel towards us, they're not only battling the expansion of space, a constant and accelerating stretching, but also carrying along with them the effects of that very motion. The faster the galaxy is moving relative to you, the more distorted their light becomes. Stretched out by this cosmic speed up, this isn't just an aesthetic effect. It fundamentally alters how we interpret the information contained within those photons. The further a photon travels, the longer it takes, and that delay accumulates over unimaginable spans of time. This leads us to the concept of cosmic look-back time. It's a truly remarkable idea. When you observe a galaxy billions of light years away, you aren't seeing it as it is now, but rather seeing it as it was. At the moment those photons were emitted, over 13.8 billion years ago. The distance to that galaxy has actually changed in the intervening time. Space itself has expanded, yet we still receive the light from that distant point, a ghostly echo of its past. Consider the James Webb Space Telescope, an instrument designed specifically to peer back into this incredibly deep past. Its infrared capabilities allow it to detect faint signals that have been stretched by redshift, essentially turning ordinary visible light into infrared wavelengths as they journey across the vastness of space. JWST observations are providing us with unprecedented glimpses into the early universe, revealing galaxies forming just a few 100 million years after the Big Bang. Looking at these distant objects is like stepping through a cosmic time machine. There's galaxy GNZ 11, for example, detected by Hubble and subsequently confirmed by JWST. It's one of the most distant galaxies ever observed, emitting light that took approximately 13.3 billion years to reach us. Think about that. Its light left that galaxy when the universe was only a few 100 million years old, less than a tenth of our current age. Similarly, we see light from galaxies like MAX 0647 JD, an even earlier candidate for one of the most distant galaxies ever found. with an estimated cosmic lookback time exceeding 14.5 billion years. These aren't just theoretical exercises in cosmology. They represent real, tangible objects, ancient islands of stars and galaxies, whose light is now finally arriving to illuminate our present understanding. It's crucial to remember that the signals we receive are shaped by countless factors: gravitational lensing, absorption by intervening gas clouds, and variations in the density of dark matter along their path. These effects further complicate the interpretation of what we see, but they don't diminish the profound implications of observing these extremely distant objects. They offer a window into a period of cosmic evolution when galaxies were just beginning to form, driven by the gravitational collapse of primordial gas clouds. And as with any journey into the unknown, there are always questions that remain unanswered, mysteries that beckon us onward. The universe continues to expand, and the horizon we perceive, the edge of our observable cosmos, is constantly receding. It's a constant dance between observation and interpretation, driven by the relentless march of time and light. It's a quiet beauty, this vastness that surrounds us, isn't it? A stillness punctuated only by the slow, inevitable expansion of space itself. And within that expansion lies an echo, a faint whisper from the universe's infancy, carried across billions of years to reach our eyes today. We are listening for it now, and what we've heard is profoundly important. We're speaking, of course, about the cosmic microwave background, often referred to as the CMB. It represents a fundamental piece of evidence in understanding the story of how everything began. And as you listen, allow yourself to drift gently into its immensity. The discovery of this faint radiation wasn't born from a grand design or a bold hypothesis, but rather a fortunate accident. In 1964, two researchers at Bell Labs, Arno Penzias and Robert Wilson, were attempting to improve the sensitivity of their radio antenna, a device designed for calibrating satellite communications. They'd effectively cleaned and checked over the equipment meticulously, expecting to find nothing beyond the usual background hiss radiating from the building itself. Yet they kept detecting a persistent, uniform signal, a low-level, almost imperceptible static that seemed to be coming from all directions in space. It was frustratingly consistent, regardless of where the antenna pointed or how it was shielded. Initially, they dismissed it as an artifact of their equipment, a stray microwave oven leak, perhaps, or dust accumulating on the satellite dish. But the signal stubbornly refused to disappear, and its uniform distribution across the sky was deeply puzzling. After much deliberation, and with some assistance from a graduate student named George Hauser, Penzias and Wilson realized that this pervasive background noise wasn't an earthly phenomenon at all. It seemed to be originating from deep space itself, coming from every point on the celestial sphere. The realization dawned upon them slowly that they had inadvertently stumbled upon radiation left over from the Big Bang, the very beginning of time as we know it. Now, this isn't just a monotone hum, it's incredibly complex. Within the CMB are tiny temperature fluctuations, minuscule variations in the intensity of the microwave radiation. These aren't random jitters. They represent the seeds of all structure in the universe, the galaxies, clusters of galaxies, and vast voids that we see today. Think of them as ripples in a pond, created by a single stone dropped into the water. The way these ripples spread outward reveals details about the early conditions of the cosmos, its density fluctuations, its cooling rate, even the presence of gravitational waves from the very moments after inflation. Scientists have meticulously mapped these temperature variations across the sky with instruments like Planck and WMAP, the Wilkinson microwave anisotropy probe. These maps aren't perfectly smooth. They show a wealth of information encoded in their unevenness. The more pronounced the fluctuations, the denser that region was at the time, and consequently, the more likely it was to collapse under gravity and form a galaxy billions of years later. It's as if the CMB is holding a faint, frozen record of the universe's first few 100,000 years. This brings us to the concept of the surface of last scattering. Imagine an enormous expanding balloon being inflated. As it expands, every point on its surface moves further away from every other point. Light emitted by a distant object will appear to redshift, its wavelength stretched out as it travels through this expanding space. Eventually, there's a distance beyond which light simply can't reach us anymore. It's been redshifted so far that its energy has faded below our detection limit. The surface of last scattering is the furthest point from which photons, the particles of light, could have reached us at one time, back when the universe was much hotter and denser. The CMB represents precisely that surface, a cosmic horizon beyond which we cannot see. It's the edge of our observable universe, not in terms of physical distance, but in terms of how far light has had time to travel to reach us since the Big Bang. The photons we observe today were emitted roughly 380,000 years after the beginning, a period known as recombination. Before that, the universe was a hot, opaque plasma of particles and radiation. As it expanded and cooled, electrons eventually combined with protons to form neutral hydrogen atoms, allowing light to travel freely for the first time. And that early light, bathed in the glow of those initial fluctuations, is now what we perceive as the cosmic microwave background. The CMB isn't just a relic. It's a window into our past, a tangible link to the very moment when the universe transitioned from a chaotic, opaque state to the relatively ordered structure we see today. As you settle deeper into this stillness, consider the incredible journey these photons have taken. Billions of years across unimaginable distances to finally reach your eyes. It's humbling, isn't it? A constant reminder that within the silent depths of space lies a story written in light. Beyond the horizon's boundary, it's a deceptively simple concept, often misunderstood. We speak of an edge, but the universe, as far as we currently understand it, doesn't possess a sharp, impenetrable rim. Rather, what defines this limit, this seemingly solid wall at the furthest reaches of our perception, is something far more subtle and profoundly related to ourselves: light itself. Specifically, It's what we call the cosmic event horizon. Think of it not as a physical barrier, but as a consequence of how we receive information from the universe, specifically how we see it. The event horizon isn't a static boundary either, though. It is constantly shifting, stretching outward alongside the relentless expansion of space itself. Consider again this analogy of the frosted window. As the glass grows further from your eye, the imperfections within it become more pronounced, gradually obscuring everything beyond its surface. Similarly, as the universe expands, the light emitted by objects located at that distant boundary, galaxies so far away, their light has only just begun its journey towards us, is stretched and redshifted to such an extreme degree that it becomes increasingly faint and eventually undetectable with our current instruments. It's not that these galaxies vanished. They simply become too dim to see, effectively slipping outside the realm of what we can observe, like a distant whisper fading into silence. This expansion isn't merely linear, it's accelerating, driven by a force we currently designate dark energy. This acceleration dramatically affects the event horizon's progress, pushing its boundary further and faster with each passing moment. Scientists suspect that this increasing rate of expansion will continue indefinitely, creating an ever-growing sphere. A sphere representing all the regions from which light has had enough time to reach you since the Big Bang. You can visualize it as like drawing circles on sand, but each circle grows larger at an accelerating pace. Now, let's imagine yourself standing here, virtually observing this cosmic frontier. You're equipped with telescopes, incredibly powerful ones, of course, that are capable of detecting light from objects billions of light years away. But even these magnificent instruments have limitations. They can only detect photons that have had sufficient time to reach us. Photons that haven't been stretched beyond recognition by the expansion of space. The further out you look, inevitably, the fewer photons arrive, and those that do are increasingly redshifted, their energy shifted towards the red end of the spectrum, much like a siren's wail as it recedes into the distance. It's important to understand that the event horizon isn't a fixed distance. It moves with every passing epoch of cosmic time. The current observable universe, the sphere from which light has had approximately 13.8 billion years to reach us, is expanding at a rate of roughly 67 miles per second per megaparsec. A megaparsec is a unit of distance equivalent to about 3.26 million light years. With each passing moment, this boundary expands, pushing the limits of what we can observe ever further out into the darkness. It's a slow, graceful unfolding, a constant reminder that our perception of reality is intimately tied to the very tools we use to perceive it. As time continues its relentless march forward, and as our telescopes become increasingly sophisticated, perhaps utilizing gravitational wave detectors, or even fundamentally new methods of observing the cosmos, we will gradually overcome some of these limitations. Future generations of astronomers may be able to detect faint signals from galaxies that are currently obscured by redshift, providing us with a clearer view of the distant universe. The instruments we design today, and those yet to come, promise a continuing refinement of this vision, allowing us to pierce further into the shadows and slowly illuminate those hidden corners. We're not reaching an edge in the literal sense, but we are steadily peeling back the layers of cosmic obscurity, revealing more and more of what lies beyond it. It's like a gradual revelation, a slow unveiling of secrets encoded within light itself. And while we may never fully grasp the scale or significance of this unseen horizon, its true nature remains one of the most profound mysteries in science. Each new observation brings us closer to a deeper understanding of our place within the grand cosmic tapestry. We've traveled across vast expanses to witness the unimaginable beauty of Nebu and distant galaxies, charting their movements through the emptiness between them. But these journeys offer only a partial view of our universe. Our local observable universe isn't isolated. It's gently tugged, subtly redirected by forces far beyond what we can directly perceive. Consider for a moment how light itself behaves. It travels in straight lines, according to the laws of physics. Yet even this fundamental building block of reality bends and curves when subjected to gravity. This phenomenon is known as gravitational lensing, and it's one of the most elegant and powerful tools astronomers possess. Massive objects, galaxies, clusters of galaxies, even individual black holes, warp the fabric of space-time around them. Light passing near these behemoths doesn't travel in a straight line. Instead, its path is deflected, distorted as if it were flowing through a lens. The closer the light travels to the massive object, the more pronounced the bending becomes, creating multiple images of distant galaxies behind the lensing body, or stretching and distorting their shapes into arcs and rings. A cosmic funhouse mirror reflecting the universe's hidden geometry. It's a subtle effect, but an incredibly revealing one, allowing us to peer through gravitational distortions to see objects that would otherwise be completely obscured. Now, let's turn our attention to a region of space that plays this gravitational role with particular intensity: the Great Attractor. Located approximately 250 million light-years away within the local supercluster. It's not an easy thing to find. The vast distances involved make direct observation incredibly challenging. We can't simply point our telescopes and look directly at it. Instead, we rely on tracking the motions of thousands upon thousands of galaxies in our vicinity. And that's where the mystery truly begins. You see, these galaxies aren't moving randomly. They are all exhibiting a peculiar stream-like pattern, a collective drift towards a specific point in space. This movement isn't caused by any galaxy directly pulling on them. It is being guided gently but persistently towards something immense and unseen. The Great Attractor's mass is estimated to be roughly 100 billion times the mass of the Sun, a staggering quantity concentrated within a relatively small volume. But what is this enormous concentration? It's primarily believed to consist of a massive galaxy cluster known as Laniakea, a region containing hundreds of galaxies bound together by their mutual gravitational attraction. However, there's also evidence suggesting that a supermassive black hole at the heart of the cluster is contributing significantly to its gravitational pull. And perhaps most intriguingly, the region continues to extend beyond the visible cluster, influencing the motion of galaxies far further afield. It's as if an invisible hand, a concentrated field of gravity, is subtly steering our neighborhood through the cosmos. This unexpected gravitational influence has profoundly impacted our understanding of nearby galaxy motions. Before its discovery, astronomers largely assumed that galaxies drifted through space in isolation, their movement determined solely by the gravitational pull of neighboring galaxies. But observations of the Hubble Space Telescope and other powerful instruments revealed a systematic deviation from this expectation, a coherent flow towards the Great Attractor. Scientists suspect that the cluster's gravity is acting like a massive tidal force, pulling these neighboring galaxies along with it. It's not an abrupt shift, rather, it's a gradual, almost imperceptible change in direction over billions of years. The way galaxies appear to accelerate or decelerate as they pass near the Great Attractor offers invaluable data points, a celestial roadmap guiding us toward a deeper knowledge of how gravity shapes the large-scale structure of the universe. The nature of this region continues to fascinate and challenge astrophysicists. We know it's there. We can observe its effects. But pinpointing its exact composition and understanding the full extent of its influence remains an ongoing endeavor. Future observations from telescopes like the James Webb Space Telescope will undoubtedly provide crucial new insights, refining our models and bringing us closer to unraveling this cosmic mystery. As you consider these distant influences on our galactic neighborhood, remember that our observable universe is a small piece in an infinitely larger puzzle, a constantly evolving landscape of gravitational interactions shaping the fate of galaxies across unimaginable distances. It is within this grand play of forces that we glimpse the true character of our place in the cosmos. A landscape of gravitational interactions shaping the fate of galaxies across unimaginable distances. It is within this grand play of forces that we glimpse the true character of our place in the cosmos. The vastness we've explored so far, the swirling nebulae, the distant stars, the individual planets orbiting suns light years away, all represent a relatively recent chapter in the story of the universe. But before these luminous objects formed, before even the seeds of galaxies emerged, there existed a period unlike anything we experience today, a time we call the Ice Age universe. Imagine a state so profoundly different from our current reality that the very concept of cold feels almost inadequate to describe it. Instead, think of an unimaginable heat combined with density beyond comprehension. A universe compressed into a volume smaller than a marble, yet containing all the matter and energy that would eventually coalesce into everything we observe. It began roughly 380,000 years after the Big Bang, a mere blink of cosmic time, and lasted for several 100 million years before slowly cooling down. Like an ice age on our own planet, albeit a drama playing out across all space and time. The fundamental conditions were brutal by any conceivable standard. The temperature was estimated to be around 10 trillion degrees Celsius, equivalent to the core of a star, 15 times hotter than the sun. And this wasn't just heat. It was energy so intensely concentrated that every point in space was essentially a singularity, an infinitely small and dense concentration of everything. Photons, the fundamental particles of light, were constantly being created and annihilated in rapid succession. A chaotic ballet of creation and destruction occurring on a scale almost impossible to fathom. It's difficult to truly grasp the sheer magnitude of this early universe. Our present is built upon the slow, quiet expansion from this fiery and dense beginning. You can picture it as an immense primordial soup, not of liquid, but of pure energy and matter, a swirling maelstrom poised on the brink of transformation. Now, amidst this chaos, tiny fluctuations, quantum variations in density began to emerge. These weren't random. They were seeded by fundamentally unpredictable processes within the early universe, thought to be driven by quantum mechanics. Consider these fluctuations as ripples in an invisible pond, incredibly small at first, but amplified over time through the relentless action of gravity. These primordial fluctuations, minuscule differences in density, grew ever so slightly larger, acting as gravitational attractors. As matter began to clump together where the density was marginally higher, it drew in more and more surrounding material, slowly building up concentrations over hundreds of millions of years. These slight variations blossomed into the large-scale structure of the cosmos. Galaxies, galaxy clusters, and vast filaments that form a cosmic web stretching across billions of light years. It is this process, the amplification of quantum fluctuations, that ultimately gave birth to the magnificent galaxies we gaze upon tonight. But gravity alone couldn't be solely responsible for shaping this cosmic landscape. A mysterious substance called dark matter played an absolutely crucial, though unseen, role. We know it exists because of its gravitational effects. It bends light around massive objects, pulls galaxies into spiral shapes, and influences the distribution of galaxies across the universe. But we cannot directly see or interact with it through electromagnetic radiation. It's estimated that dark matter makes up approximately 85% of all the mass in the universe. Because of its immense gravitational pull, it started clustering before ordinary matter, the stuff that makes up stars and planets, even while the early universe was still incredibly hot. These pre-existing clumps of dark matter provided a scaffolding around which galaxies could form. They acted as gravitational wells, drawing in surrounding gas and dust, effectively accelerating galaxy formation by creating denser regions for star formation to occur. Without this invisible hand guiding the process, the visible structures we observe would have likely been far less complex and fragmented. These first galaxies weren't like the orderly spirals or ellipticals you see today. They were incredibly chaotic, merging frequently, constantly colliding with each other in a turbulent dance of gravitational interactions. They ejected stars into intergalactic space, created immense bursts of star formation that flooded the universe with light, then slowly settled down as gravity continued to bind them together and shape their forms. As the universe cooled slightly, though remaining incredibly hot by our standards, ordinary matter began to condense and form stars, planets, and eventually rocky worlds like our own Earth. So the Ice Age universe wasn't simply a prelude to the beautiful galaxies we see now. It was the crucible where the very seeds of cosmic structure were forged, setting in motion the processes that would ultimately lead to the emergence of everything you observe around you. From the faint glow of distant quasars to the intricate details of our own solar system. And as we continue to probe this ancient epoch with increasingly powerful telescopes and sophisticated simulations, we are slowly beginning to unravel its deepest secrets, gaining a more complete understanding of the origins of our universe and our place within it. It's a humbling experience to realize that our current knowledge represents but a tiny flicker in the vast expanse of cosmic time. And as we delve deeper, particularly into questions like those surrounding dark energy, we find ourselves confronted with complexities that challenge even the most established theories. Let us now consider how observations of the faintest, furthest objects have revealed one of these profound mysteries: the accelerating expansion of the universe. For decades, astronomers meticulously studied distant supernovae, those brilliant explosions marking the deaths of massive stars, seeking to determine their intrinsic brightness, what scientists call their absolute magnitude. By comparing this absolute magnitude with their observed apparent magnitude, which is how bright they appear from Earth, we could calculate their distance. Then, by measuring the redshift, the stretching of light waves as space itself expands, we could also ascertain how quickly these supernovae were receding from us. Initially, it seemed that the universe's expansion was gradually slowing down, as expected given Newton's law of universal gravitation. It anticipated a gradual deceleration towards a stable state. However, beginning in the late 1990, observations of type Ia supernova, unusually consistent and bright stellar explosions, yielded startling results. these supernovae appeared fainter than they should have been, given their redshift. This indicated that they were further away than previously estimated, not just farther, but receding at an increasing rate. It was as if the universe wasn't simply expanding, but actively speeding up its expansion over time. The evidence became undeniable. The expansion of our universe isn't slowing down, it is accelerating. It presented a fundamental shift in our understanding of cosmic evolution. The discovery of this accelerated expansion spurred tremendous theoretical investigation and proposed explanations for what could be driving this relentless push outwards. One dominant hypothesis centers on vacuum energy, also known as dark energy. The concept stems from quantum field theory, suggesting that even empty space isn't truly empty, but teeming with fluctuating quantum fields, virtual particles constantly popping into existence and disappearing almost immediately. These fluctuations would impart a certain amount of energy to the vacuum, creating a negative pressure that effectively pushes everything apart. It's a deeply counterintuitive idea, an inherent property of space itself driving expansion, rather than gravity pulling inwards. Other intriguing possibilities include cosmic strings, hypothetical one-dimensional topological defects left over from the early universe, or modifications to Einstein's theory of general relativity at large scales. Perhaps our understanding of gravity needs revision, and the equations we currently use to describe it are incomplete or inaccurate when applied to the enormous distances involved in the observable universe. Scientists suspect that these strings could create a repulsive force as they move through space, contributing to the accelerated expansion. And still others explore the idea of quintessence, another dynamic energy field whose density changes over time and influences the expansion rate. It is important to appreciate that these theories are, at present, highly speculative, driven by mathematical models and theoretical predictions, awaiting potentially revolutionary observational confirmation. The implications of dark energy for the ultimate fate of the universe are profound, and rather unsettling. If this accelerated expansion continues indefinitely, and current observations strongly suggest it will, the observable universe will eventually become effectively isolated from everything beyond. Galaxies will continue to recede at ever-increasing speeds, becoming increasingly difficult to see or interact with. The light from distant objects will be stretched so far that it shifts towards the red end of the spectrum. Its energy decreases, and it ultimately fades away. Within a finite timescale, perhaps tens of billions of years, the observable universe will essentially become a dark, isolated bubble adrift in an ever-expanding void. However, there's also the possibility, though less favored currently, that this accelerated expansion will eventually slow down or even reverse. If dark energy's nature were to change over time, perhaps becoming stronger, the repulsive force could weaken, and gravity might eventually regain its dominance, leading to a contraction of the universe in a phenomenon known as the Big Crunch. The future, viewed through the lens of dark energy, remains shrouded in uncertainty. It is an active area of intense research, fueled by ongoing observations from increasingly powerful telescopes and sophisticated simulations that attempt to map out this cosmic dance with ever greater detail. The very notion of a horizon, a boundary beyond which we cannot see, becomes profoundly relevant as we contemplate the accelerating expansion and its potential consequences for our place within everything. The very notion of a horizon, a boundary beyond which we cannot see, becomes profoundly relevant as we contemplate the accelerating expansion and its potential consequences for our place within everything. Now, let's turn to how we begin to comprehend that vast, unseen space. How we start to chart the edges of what we can observe, not through sight alone, but through the subtle whispers of gravity itself. The universe is a deceptive architect. It presents a dazzling display of light and color, while concealing the bulk of its substance, something called dark matter. It's an enduring mystery, this invisible component, yet one that increasingly dominates our understanding of cosmic structure. Scientists have long suspected the existence of something beyond what we can directly observe. The key to unlocking its presence lies in a phenomenon known as gravitational lensing. Imagine bending light. It's a fundamental property of space and time, dictated by Einstein's theory of general relativity. Massive objects, planets, stars, galaxies, warp the fabric of space-time around them. And this warping fundamentally alters the paths that photons, or particles of light, take as they travel through the universe. Now, dark matter also possesses mass, and therefore it warps space in a similar way. When a galaxy lies between you and a distant quasar, an immensely luminous galaxy at the center of another galaxy, the light from the quasar will bend around the intervening galaxy's gravitational field. The degree of bending depends on how much mass is present along that line of sight, including the dark matter that isn't visible to us. This is like looking through a magnifying glass. The more massive the object, you're looking through, the greater the distortion. By meticulously analyzing these distortions, the subtle shifts in the quasar's light spectrum, the stretching and magnification of its image, scientists can infer the distribution of dark matter within that intervening galaxy, and even across vast distances. It's a remarkably indirect method, but incredibly powerful, because it allows us to map something we fundamentally cannot see directly. Over the past several decades, astronomers have employed some of the most ambitious projects ever conceived to gather this data. One particularly crucial effort is the Sloan Digital Sky Survey, or SDSS. This collaborative undertaking has meticulously mapped hundreds of millions of galaxies and quasars across a significant portion of the southern sky. The SDSS doesn't just provide images, it also measures the redshifts of these distant objects, essentially how much their light has been stretched by the expansion of the universe. Redshift is intimately related to distance, providing a powerful tool for understanding the large-scale structure of the cosmos. By analyzing the gravitational lensing effects observed in conjunction with the SDSS data, scientists have begun to build a preliminary model of dark matter's distribution a faint, ghostly outline etched across the sky by its influence on visible light. But mapping the unseen is far from complete. The current models derived from these surveys represent only a rough sketch, a statistical average over a huge volume of space. To create a truly detailed 3D map, scientists are turning to even more sophisticated techniques and new generations of telescopes. Projects like the Dark Energy Survey, DES, and the Vera C. Rubin Observatory, Legacy Survey of Space and Time, LSST, are pushing the boundaries of what is possible. The LSST, in particular, will provide an unprecedented level of detail, observing nearly every square degree of the night sky for years to come. The goal isn't simply to count galaxies. It's to measure their positions with incredibly high precision and to map the way that light bends around them, essentially creating a cosmic shadow map of dark matter. Future simulations will combine data from multiple telescopes and techniques, refining our understanding of how dark matter has shaped the development of galaxies and the overall structure of the universe. This process will allow us to move beyond statistical averages and start to perceive the complex filaments and voids that constitute the cosmic web, the scaffolding upon which everything is built. It's a slow, painstaking endeavor, requiring both immense computational power and careful observation. Yet, with each new piece of data, we are gradually peeling back the layers of mystery surrounding dark matter, moving closer to a truly comprehensive understanding of our universe's composition and evolution. The horizon, once an abstract concept, is slowly revealing itself, not as a barrier, but as a limit of our current observational capabilities, a challenge that drives us to develop ever more ingenious ways to probe the depths of space and time. The vastness of space, once perceived solely through the lens of visible light, is now being unveiled by a fundamentally different sense, one that detects the very fabric of space-time itself. We're talking about gravitational waves, ripples propagating outward from cataclysmic events across billions of years, offering perhaps the most direct line to understanding the universe as it was in its infancy. These aren't sound waves traveling through air. They are distortions in the geometry of space-time. Echoes born from the accelerations of massive objects, black holes colliding, neutron stars merging, or even the very first moments after the Big Bang. Instruments like LIGO and Virgo, located thousands of miles apart on Earth, tirelessly listen for these subtle shifts in distance, precisely measuring changes so minute they are smaller than a single proton. They effectively act as giant, exquisitely sensitive interferometers, bouncing laser light between mirrors separated by kilometers, detecting the minuscule time delays caused by the passage of a gravitational wave. Each blip, each correlated detection across both observatories is a tentative confirmation that we are truly hearing whispers from the deep past, the echoes of events stretching back to within a fraction of a second after the universe began. It's remarkable to consider that these detectors, marvels of human ingenuity, are capable of registering disturbances so incredibly faint they represent distortions in space-time itself, a concept far removed from everyday experience. Now, let us turn our attention towards something even more profound: primordial gravitational waves. These aren't the end products of stellar mergers. Instead, they are believed to be direct remnants of inflation, a period of extremely rapid expansion that occurred within the first fraction of a second after the Big Bang. The leading idea is that during this inflationary epoch, quantum fluctuations in the very fabric of space-time were stretched to unimaginable scales, creating ripples that propagated throughout the universe like sound waves in a gigantic ocean. These primordial gravitational waves would have carried with them a unique imprint on the cosmic microwave background radiation, the afterglow of the Big Bang. We've now detected this imprint, though it's incredibly faint and difficult to discern amidst the noise of other cosmological processes. The patterns we observe are akin to faint brush strokes across the canvas of the universe, telling us about the conditions present during inflation, offering a glimpse into the very earliest moments of existence. It's an extraordinary connection. that ripples generated in the immediate aftermath of creation can still be detected today, providing valuable data for scientists attempting to piece together the grand puzzle of the universe's origins. The scale of this connection is humbling, suggesting that events occurring at such extreme energies and distances are not entirely beyond our ability to study. And it's not just looking at the CMB that's yielding insights. There's growing evidence suggesting a possible relationship between gravitational wave signals and the patterns we see in the cosmic microwave background, specifically certain types of non-Gaussianity, subtle statistical irregularities in the temperature fluctuations of the CMB could be generated by interactions between primordial gravitational waves and ordinary matter during the early universe. Imagine an ocean wave gently disturbing the surface of a lake. The ripples would cause a chaotic scattering of the water molecules, creating a complex pattern. Similarly, primordial gravitational waves might have subtly altered the distribution of matter in the early universe, leaving their imprint on the CMB as these statistical irregularities. Detecting and characterizing this connection is a major focus for current research. Scientists are carefully analyzing the data from gravitational wave observatories alongside sophisticated maps of the CMB, searching for correlations that could reveal the mechanisms governing the evolution of both the very small and the very large. These aren't merely competing lines of inquiry. Rather, they represent complementary approaches to understanding the same fundamental processes, pushing us ever closer to a more complete picture of the universe's formative years. Furthermore, as gravitational wave detectors become increasingly sensitive, we can anticipate uncovering even more elaborate patterns and signatures, adding layers of complexity and richness to our knowledge of the early cosmos. The search for these subtle echoes continues, representing one of the most exciting frontiers in modern cosmology, offering a completely new window into an era shrouded in mystery. It's a testament to the persistent curiosity that drives us to explore the boundaries of what is known, and perhaps more importantly, the boundaries of what we can know. As we look back toward Earth, a pale blue marble suspended within this vastness, it's easy to lose sight of just how profoundly strange the universe truly is. We've spent decades charting its movements, attempting to capture echoes of events billions of years distant. A frustrating, beautiful exercise in peering backward into time. And yet, at the very edge of our reach, something remarkable and deeply humbling begins to reveal itself. A fundamental limit to our understanding, expressed not as an insurmountable barrier, but as a gentle curvature in the fabric of what we can observe. We are now entering a discussion about the Hubble sphere, a concept born from the elegant mathematics described by Edwin Hubble himself, and its implications for our exploration into the deep unknown. Hubble's law, a cornerstone of modern cosmology, describes a simple yet profound relationship. The farther away a galaxy is from us, the faster it appears to be receding. It wasn't an initial assumption. Rather, it emerged from careful measurements of redshifting, the stretching of light wavelengths as objects move away from us. This redshift isn't just a visual effect, but a direct consequence of space itself expanding. Imagine two ships sailing away from each other on a rubber sheet. As the sheet stretches, the distance between the ships increases, and the relative speed at which they are moving apart also grows. Similarly, galaxies embedded within an ever-expanding universe carry this expansion along with them. The further in distance a galaxy is, the greater its recessional velocity due to this cosmic expansion, a velocity approaching the speed of light. Now, consider how this plays out across immense distances, over billions of years. These speeds continue to accelerate, carrying galaxies beyond our ability to ever observe them. No matter how powerful our telescopes become, the Hubble sphere isn't a physical object, but rather a conceptual boundary defined in terms of distance. It represents the point in space where the recessional velocity of an object, typically a galaxy, exceeds the speed of light. And while we know that nothing within space-time can travel faster than light, the expansion of space-time itself allows these distant galaxies to recede from us at speeds exceeding this cosmic limit. This might seem counterintuitive. It's not as if the galaxies are launching themselves into space. Rather, the very fabric of reality between us is stretching so rapidly that they simply vanish from view, becoming forever inaccessible. The further you go beyond this sphere, the more rapidly things recede towards a future where they will effectively disappear from our observable universe. It's important to understand that the light emitted by these objects was once headed toward us. It's traveling at the speed of light, as it always was. But its journey is simply destined not to reach us. This concept profoundly affects how we consider the study of distant galaxies. For centuries, astronomers dreamed of reaching these far-off realms, imagining journeys across immense cosmic distances. The Hubble Space Telescope, and now the James Webb Space Telescope, have dramatically expanded our observational capabilities, pushing back the boundaries of what we could detect. But even with these extraordinary instruments, there's a fundamental limitation imposed by the Hubble sphere. We can observe galaxies within its reach with increasing detail and clarity, mapping their structures, studying their star formation, analyzing their composition. But any attempt to study galaxies beyond this boundary will always be a one-way conversation. We receive light from them, never any direct response. The light is traveling towards us across an expanding universe. The distance it must cover continues to increase as time passes. It's not a cause for despair, but rather a reorientation of our perspective. It compels us to appreciate the incredible distances involved, distances that are truly mind-boggling. These galaxies remain real in a sense. They continue to exist and evolve. Their processes unfolding independently of our ability to observe them directly. Our understanding of the universe is shaped by the light we do receive, by the echoes traveling across this expanding cosmos, a constant reminder that there's much more beyond the limits of what we can see, and an enduring invitation to continue seeking out new ways to illuminate the darkness. We may never be able to visit these distant galaxies. It is perhaps not the intention at all. The true exploration lies in deciphering their light, piecing together a history from the subtle whispers it carries across the void, revealing the grand narrative of cosmic evolution. The light from quasars stretches across almost unimaginable distances, a testament to the sheer scale of time and space. These ancient beacons aren't simply distant stars, but rather windows into an era when the universe was still finding its footing, a period shrouded in increasing darkness as the cosmic web began to knit itself together, drawing matter towards forming galaxies. Consider this: quasars formed primarily during the epoch of reionization, a time roughly between 180 and 250 million years after the Big Bang, when the first stars and galaxies ignited, releasing a flood of ultraviolet light that essentially stripped the hydrogen gas from the early universe, making it transparent to longer wavelengths. It's difficult to fully grasp the density of this period. You could argue that many of the galaxies we see today were coalescing out of vast clouds of intergalactic gas, a churning soup of hydrogen and helium dust illuminated by these nascent stars. The very process of galaxy formation itself generated the conditions necessary for quasar birth. Massive black holes, behemoths residing at the centers of early galaxies, began to accrete matter, gas, dust, even entire smaller galaxies, drawing it inwards in a relentless spiral toward their event horizons. This spiraling material, heated to extraordinarily high temperatures as it approached the black hole, creating an accretion disk, a swirling vortex of superheated plasma that radiates with unbelievable power. As this matter plunged into the black hole's maw, releasing its energy in the form of jets and radiation, these quasars became intensely bright, shining with a luminosity that far outshines any galaxy they inhabit. Now, let's talk about that brightness, a truly astonishing characteristic of these cosmic lighthouses. A typical galaxy might emit a few 100 billion times the energy output of our sun. But a quasar, an active galactic nucleus, as these objects are officially termed, can unleash energies exceeding 1 trillion times the solar luminosity. This isn't simply an increase in brightness. it's a fundamentally different kind of radiation, primarily coming from the accretion disk itself. The immense gravitational forces compressing the material convert potential energy into kinetic energy and then into heat, heating it to temperatures exceeding 10 billion degrees Celsius. It is at these extreme temperatures that protons and electrons collide with enough vigor to produce synchrotron radiation, a type of electromagnetic radiation created by charged particles spiraling around magnetic fields within the accretion disk. Think of it like a cosmic light show, a ballet of fundamental particles performed on an unimaginable scale. The immense energy output isn't constant. It ebbs and flows as the material feeding the black hole fluctuates, leading to dramatic variations in quasar brightness over time, which researchers carefully monitor. But here's where things get particularly fascinating. Studying these ancient lights provides a crucial key to understanding how galaxies themselves evolved. Because quasars are intrinsically linked to their host galaxies, the massive galaxy at whose center they reside. Observing changes in quasar luminosity and activity can reveal details about the galaxy's evolution at vastly different epochs. The more active a quasar, frequently, the more gas is being funneled into the central black hole. This process essentially starves the galaxy of fuel for its own internal star formation, effectively halting or slowing the creation of new stars. By observing how galaxies evolve in relation to their quasars, astronomers can infer whether they are actively growing, merging with other galaxies, or simply running out of material to feed their central black holes. Furthermore, the light from distant quasars allows us to probe the distribution of dark matter, the invisible substance that dominates the universe's mass, through a phenomenon called gravitational lensing. The immense gravity of a massive galaxy bends and distorts the light coming from a more distant quasar, creating multiple images and warping its shape. Analyzing these distortions provides a map of the underlying dark matter distribution, offering an unprecedented glimpse into the unseen scaffolding that shapes the cosmos. Studying these objects isn't merely about understanding individual celestial bodies. It's about constructing a comprehensive timeline of cosmic history, tracing the grand dance of stars, galaxies, and black holes across billions of years. Let us now turn our attention to a concept that stretches the bounds of what we can directly perceive. The possibility, perhaps even the inevitability, of a multiverse. It's a notion initially whispered by theoretical physicists, gradually gaining momentum as our understanding of cosmology has deepened. Consider for a moment the immense scale of everything we do observe. The observable universe, defined by the distance light, has had time to travel since the Big Bang. A sphere encompassing roughly 46 billion light years in every direction. But what lies beyond that boundary? What if our entire reality is but one bubble within an infinite sea of other universes, each with its own set of physical laws and constants? The idea isn't rooted in idle speculation. It's directly linked to inflationary cosmology, the prevailing theory describing the rapid expansion immediately following the Big Bang. Inflation suggests that this initial expansion wasn't uniform across all space, but rather occurred at vastly different rates in different regions. This leads naturally to the possibility of bubble universes budding off from one another, each with potentially radically altered characteristics. The notion is elegantly supported by observations of the cosmic microwave background, the faint afterglow of the Big Bang. Tiny temperature fluctuations within this background suggest that our universe isn't perfectly smooth. It contains subtle patterns consistent with collisions between bubble universes in a larger multiverse landscape. It's important to understand, though, that these collisions, if they ever occurred, would have left their mark, a faint imprint on the CMB. And those imprints are precisely what scientists are searching for today with increasingly sophisticated telescopes. These aren't pictures of other universes directly, of course. It's a statistical echo, a ghost of interactions long past. Now, how do we even begin to explore such vast, hypothetical realms? The answer, surprisingly, lies in the tools of our own creation. Simulations, computer modeling, has become an indispensable part of scientific investigation across countless fields, and cosmology is no exception. Researchers are using supercomputers, machines capable of performing trillions of calculations per second, to create increasingly complex models of the universe, exploring scenarios far beyond the reach of direct observation. These simulations attempt to recreate the conditions immediately following the Big Bang, or to model the dynamics of a potential multiverse, allowing scientists to test different cosmological models against observed data in a controlled environment. We're seeing powerful examples now, generated with impressive fidelity, using tools like SDXL and Flux, crafting visual representations of what might exist beyond our immediate view. Imagine, if you will, a three-dimensional rendering based on current theories concerning dark energy, that mysterious force driving the accelerating expansion of our universe, combined with ideas about how extra dimensions might manifest themselves. The resulting image isn't photographic. It's an artistic rendition informed by mathematical models and theoretical physics. It depicts a swirling expanse of color, textures suggesting varying densities and energies, hinting at landscapes utterly unlike anything we could ever encounter physically. This is fundamentally a framework, a way to ask, if dark energy behaves in this particular manner, what might the structure of space-time look like on scales vastly larger than our observable universe? It's not a prediction of reality, but rather a tool for investigation. Think about it. If the fundamental constants of physics, gravity, electromagnetism, the mass of an electron, varied slightly across different universes, would we even be here to observe them? The possibility suggests that our very existence is a statistical anomaly, a fortunate accident within a vast multiverse where conditions are just right for life. Simulations allow us to explore these what-if scenarios with remarkable precision, testing the sensitivity of cosmological models to these seemingly minor variations, exploring whether a universe with slightly stronger gravity would collapse in on itself, or one with weaker gravity would remain forever frozen and lifeless. The implications of such explorations are profound. They challenge our anthropocentric view of the cosmos, reminding us that what we perceive as fundamental laws might simply be local conditions within a much larger, more complex reality. Studying these simulated universes isn't about uncovering definitive answers. It's about refining our questions and developing increasingly sophisticated tools for probing the deepest mysteries of existence, eventually inching closer to a comprehensive understanding of not just this universe, but perhaps ultimately everything that exists beyond. And now we find ourselves turning our gaze further outward, toward horizons previously obscured by the limitations of existing technology. The quest to understand what lies beyond the visible simply does not pause. It evolves, driven by an enduring human desire to know, a steady commitment to unraveling the intricate tapestry of existence. The instruments available to us today, remarkable as they are, the Hubble Space Telescope, the James Webb Space Telescope, already revealing astounding details, have provided invaluable glimpses into the cosmos. But they represent stepping stones, crucial advancements that nonetheless operate within defined boundaries. It is with this understanding in mind that we consider the next generation of space telescopes, ambitious projects poised to dramatically enhance our perspective and perhaps even redefine what it means to reach for the unseen. Among these transformative endeavors stands the Roman Space Telescope, an infrared observatory specifically designed to study dark matter and exoplanets. Its mission isn't driven by a desire simply to see more of the universe, but rather to understand what is making up the vast majority of it, something we still know remarkably little about. Roman boasts a unique wide field instrument, WFI. Think of it as an enormous digital eye, capable of scanning huge swaths of sky simultaneously, covering several 100 times more area than Hubble could achieve in its field of view. This ability is particularly critical for detecting faint, distant galaxies and mapping the distribution of dark matter through gravitational lensing. The bending of light around massive objects, as scientists suspect. This detailed map will paint a far richer picture of how structures are assembled throughout cosmic time, offering insights into galaxy evolution and the formation of large-scale cosmic web. The power of WFI extends beyond just sheer area coverage. It's designed to operate at a wavelength range significantly longer than that of Webb specifically targeting infrared light. This is crucial because much of the light from incredibly distant galaxies has been stretched out, redshifted by the expansion of the universe to appear in the infrared spectrum. By observing this faint infrared glow, Roman will be able to detect objects that are so far away that they would remain invisible to even the most powerful visible light telescopes. Imagine trying to see a firefly across a vast plain at midday. You'd need specialized equipment and a focused approach. Similarly, Roman is equipped with sophisticated filters designed to isolate specific wavelengths of light emitted by these distant galaxies, allowing scientists to identify their composition, age, and even potentially their origins. Beyond dark matter mapping, Roman's capabilities also extend to the search for exoplanets, planets orbiting stars other than our Sun. The telescope will employ a technique called microlensing, where the gravitational field of a foreground star briefly bends and magnifies the light from a distant background planet, revealing its presence. This method is particularly effective at detecting smaller, rocky planets that might be similar in size to Earth, bolstering the hunt for potentially habitable worlds beyond our solar system. The data gathered by Roman won't simply confirm the existence of these planets. It will provide detailed information about their atmospheres, searching for telltale signs, biosignatures of life. Looking further ahead, projects like the Extremely Large Telescope, ELT, currently under construction in Chile, are adding even greater complexity and scale to our observational capabilities. The ELT's unprecedented light-gathering power and adaptive optics will allow it to study individual stars in incredible detail, probing their internal structures and searching for planets orbiting them. combined with future missions that incorporate space-based interferometry, essentially linking multiple telescopes together. We could effectively create a single telescope the size of a planet. The potential for groundbreaking discoveries arising from these advancements is truly profound. It's possible we will come to understand how galaxies formed and evolved in their earliest phases. We might detect signs of the first stars, incredibly massive objects that seeded the universe with heavier elements. Perhaps within the data flows, hidden amongst the statistical noise, lie hints, subtle but undeniable, of civilizations beyond our own. Ultimately, these future observatories represent more than just upgrades to existing technology. They are a testament to human curiosity and our unwavering pursuit of knowledge. Tools designed to steadily push us closer to a comprehensive understanding of not just this universe, but perhaps, ultimately, everything that exists beyond. And as we continue to build these instruments, refining the techniques for observing them, we also refine our models, our theories, our very way of thinking about what's possible in the vast expanse of space and time. Here now, there's a pause, a stillness that mirrors the emptiness we've just witnessed stretching out beyond comprehension. The image shifts slightly, resolving back into view, a breathtaking vista of our own world, suspended in the black velvet of space. It's a small sphere, impossibly blue and white against an infinite darkness. Yet it holds everything you know, everything you are. Consider for a moment the sheer improbability of this scene, painted across light years from where we stand. The sun, a furious heart of energy, bathing continents in warmth, while here, in the void, the last traces of light from distant galaxies are still traveling towards us, arriving now as faint whispers, echoes of events that transpired billions of years ago. You can almost feel the weight of that journey, the immense timescale of cosmic history laid bare before you. Looking back at Earth evokes a fundamental shift in perspective, a humbling realization woven into the fabric of your being. We tend to inhabit our worlds with a certain sense of centrality, of importance, and rightfully so. We are undeniably alive here. But from this distance, suspended between the observable universe and the unknowable beyond that feeling becomes delicate. It isn't diminished, not truly, but it is tempered by an understanding of scale that defies easy grasp. The distances involved in simply reaching this viewpoint, hundreds of miles above our atmosphere, are staggering, a testament to human ingenuity and ambition. Yet, as you trace your vision along the curve of the Earth, noting the continents drifting like islands on an endless ocean, it's not just those distances that are remarkable. It's the sheer concentration of life, of potential, contained within this single planet, a tiny speck in a universe teeming with countless possibilities. The vastness of space reminds us of our relative insignificance, but simultaneously reveals the extraordinary significance of what we are, and the unique circumstance of consciousness evolving here. Scientists suspect that there may be billions upon billions of planets orbiting other stars, perhaps many harboring their own forms of life. And yet, for all this potential, for all these distant worlds, you remain grounded in this one place, inextricably linked to this blue marble, suspended in darkness. It becomes clear then, not as a cause for despair, but as a profound source of wonder, a preciousness born from perspective. The universe doesn't care about our anxieties or our ambitions on a local scale. It simply is an intricate and beautiful tapestry woven across unimaginable distances and eons of time. And yet, within that grand design, there is space for us to observe, to learn, to question, and perhaps one day to understand more fully the processes that brought us into existence, or maybe only to appreciate the marvel of simply being here as you are now. We've spent this journey exploring the edges of what we can currently see, tracing the limits of our knowledge through telescopes and equations, before engaging in these endeavors to build these instruments, refining the techniques for observing them. We also refine our models, our theories, our very way of thinking about what's possible in the vast expanse of space and time. The edges of the observable universe, a boundary defined by the distance light, has had since the Big Bang, represents represent not an end point, but a limit to our current senses and methods. Beyond that horizon lies everything else, unseen and perhaps forever unreachable. Yet even this apparent endpoint fuels further inquiry. The pursuit of understanding isn't about reaching a destination. It's about following the threads of curiosity, continuously pushing the boundaries of what is known. The exploration continues, driven by an inherent human need to seek answers where questions remain. New technologies, gravitational wave detectors, advanced imaging satellites like James Webb, are constantly reshaping our understanding, peeling back layers of cosmic mystery and revealing previously hidden structures. We look toward the future with a cautious optimism, recognizing that every discovery brings not only new knowledge, but also entirely new sets of questions. The universe is a boundless library filled with untold stories. It's simply a matter of developing the skills to read them. And as you reflect on this journey through the cosmos, consider the legacy you leave behind, your own pursuit of comprehension, your contribution to expanding that collective human vision. There remains a fundamental sense of connection to everything, a silent awareness that we are all part of something larger than ourselves. It's not about finding definitive answers or establishing dominance over the universe. It's about embracing the mystery and appreciating the delicate beauty of our place within it. Letting go of the need for finality can be profoundly liberating. As the image fades back to Earth, a simple reminder of home amidst the grandeur of space, allow yourself to feel, to simply be grounded in this moment, and trust that the questions we ask will always be answered by the quiet wonder within, you and the vastness waiting to reveal itself. As we gaze outward now, past the swirling galaxies, beyond the faint glow of distant quasars, it's easy to feel a profound sense of solitude. Yet within that vastness, our own world remains, a blue marble suspended in an unimaginable sea. The edge we've traced is but a point on the curve of existence, a boundary defined by the limits of light itself. Consider the timescales involved, billions of years have flowed into moments as we perceive them. And still, this journey continues, unfolding with every passing second. Perhaps there is no true end, only an endless horizon stretching toward something beautiful and unknown. Thank you for spending this time among the stars with me. If you enjoyed the journey, a gentle like and a subscribe help more quiet dreamers find their way here. Until next time, rest well and keep wondering about the cosmos. Good night.